Good day. I will be discussing assignment 6. Here is the first question of assignment 6. F is defined as x squared minus y squared plus x, and we want to determine the value of p such that the tangent to the surface z equals f of xy at the point 1p is parallel to the plane 3x plus 8y equals z. So we have two planes, the tangent plane and this other plane, and we want the two planes to be parallel. The first job is we need the normal of both planes. So let's start off by saying we want the normal of the tangent plane. So to find the normal of the tangent plane, we need partial derivatives. So we know, because we have a formula for f, that f partial x is we differentiate x squared minus y squared plus x with respect to x. If we do that, we get that this turns out to be 2x plus 1. So f partial x at the point 1p evaluates to the value 2 times 1 plus 1, which is 3. Likewise, f partial y turns out to be the partial derivative of x squared minus y squared plus x, and that works out to be minus 2y. So f partial y at the point 1p works out to be minus 2p. So normal of tangent plane, and that's what we care about, is, let's call it n1. The formula is minus f partial x at point 1p minus f partial y at the point 1p, comma 1. And we've worked out that this turns out to be minus 3 2p, comma 1. And now normal of the other plane, so the normal of 3x plus 8y minus z equals 0 is, let's call it n2. And so it's a coefficient of x, it's a coefficient of y, and it's a coefficient of z. And now it's given that the two planes are parallel. Now this is very important, so let's write that down. Planes are parallel if and only if there exists a real number k such that, what does it mean for planes to be parallel? Yep, you're quite right. That means that n1 equal to k times n2. And now we're in business because we know that the normal of the first plane is minus 3 2p1. And we know that the normal of the second plane is 3 8 minus 1. Now we look at the first components, the second components, and the third components. And if we look at the third components, we see k is equal to minus 1. And by looking at the second components, we get that 2p is equal to minus 8, which means that p is equal to minus 4. So this was not a difficult question. So again, the normals were important, and you had to know how to find the normal of the tangent plane, which is this formula, minus fx minus fy, comma 1. So that is worthwhile knowing. All right, we're happy with this question. Let's move on to the second question. So the second question was, find the vector equation of the line perpendicular to the surface z equals x squared plus xy over y squared plus 1 at the point 1, 1, 1. Now clearly this point 1, 1, 1 is on the surface, because if x is 1, y is 1, you substitute it into the expression, it evaluates to z is equal to 1. Now again, we want the normal of the tangent plane. So to find the normal of the tangent plane, we are again interested in partial derivatives. So let's calculate partial derivatives again. So we need f partial x, and now f is a fraction, so we're going to need the quotient rule to work out the derivative of f partial x. And if you apply the quotient rule, it's the derivative of the top, you agree, times the bottom minus the top times the derivative of the bottom all over the bottom square. And if you now plug in the 0.11, I'm going to leave it for you to verify. You get 6 over 4, which you can simplify to 3 over 2. Likewise, you need f partial y. Again, because f is a fraction, you need the quotient rule. So it is the derivative of the top with respect to y times the bottom minus the top times the bottom. So again, you differentiate the bottom with respect to y all over the bottom squared. And then we need f partial y at 0.11. And if you do the calculation, check that you agree, you get minus 2 over 4, which is a half. And now we're in business because now we can say normal of tangent plane is, let's call it n, which is minus f partial x at 0.11 minus f partial y at 0.11, comma 1. And here it evaluates to minus 3 over 2 minus, that was minus a half, so this becomes plus a half, comma 1. So now we have a surface and we have the 0.11, and at the 0.11 we created the tangent plane, and now we have the normal of the tangent plane, the surface at the 0.11. Now n is perpendicular, so you're looking for the vector equation of the line that's perpendicular to the surface at the 0.11. So we're looking for a line that passes through the 0.11 and it has to be perpendicular to the plane. So if that means that the direction of the line is a scalar multiple of the normal. Draw a picture to convince yourself that you agree with this. So we're in business, so now we can talk about the line. So we can say the line is equal to x is equal to point plus t times the direction, which is n, where t is a real number. And so we know that the line must go through the 0.111, and we know that the normal is minus 3 over 2 a half 1, where t is a real number. You could have used any multiple of the direction. So some students might have written it's 111 plus t times minus 3, double it becomes 1, 2, where t is a real number. So again, this is the equation of the straight line. Again, you don't have to use the 0.111, you could have used any other point on the line, but why bother if we already know that the line passes through the 0.111? So don't do unnecessary calculations if you don't need to. So this was not a very difficult question. So just if the line is perpendicular to the plane, then it means that the direction of the line is the scalar multiple of the normal. All right. So that was another easy-ish question. And so for the very last question, it deals with the chain rule when you have loads of variables. So here we have lots of information. And for this question, I'm going to take the value alpha equals 5. So that means that f partial u at the point 2, 3 evaluates to 5 plus 1, which is 6. And f partial v at the point evaluates to 5 plus 5, which is 10. Now, there are so many variables here. So very important, when you get these kind of questions, step 1, draw a tree diagram. Before you do anything else, you've got to draw a tree diagram. Otherwise, you're going to lose yourself in the sea of variables. So let's start off with. So f uv, that is w. All right. So f is the main guy. Now we can clearly see f is a function of u and v. And now, looking at this expression, we can see that u is a function of s and t. Likewise, we can see that v is a function of s and t. So we can say ultimately W is a function of S and T, so it makes sense to talk about W partial S and W partial T, because at the end of the day, W is a function of S and T. So if we draw a tree diagram, we can say S and T are the leaves. All right, now we are asked to calculate Ws at the point 1, 0 and Wt at the point 1, 0. So let's start off with the first task. So we start at W and we're looking at all the paths ending at S. So there's a path ending at S and there's another path ending at S. So we can see that Ws is the first path, which is going from F to U and then from U to S. And then the second path goes from F to V and then from V to S. So that is the first path. We have an expression. Now that we have an expression, now we can say W is 0.10 equal to the F partial U at the point 23, US at the point 10, F partial V at the point 23, and then V is at the point 10. So not to lose yourself, it's sometimes useful to have a column here called values. So here we have that S corresponds to 1 and then T corresponds to 0. So you can see that if S is 1 and T is 0, that U10 evaluates to 2, so this corresponds to U is equal to 2. Likewise, if S is 1 and T is 0, then V10 corresponds to 3, that means that V is equal to 3. And this is why I use the value 2 and 3 here, because if S corresponds to 1 and T corresponds to 0, then U evaluates to 2 and V evaluates to 3. Hence why we have this. So we have two equations here. This is a general expression, and here is when we have specific values. And now we're in business because we are given that F partial U at this point is 6. U partial S at this point evaluates to 4. F partial V at this point is given as 10, and V partial S at this point corresponds to minus 2. So we end up getting 6 times 4 plus 10 times minus 2, which is 24 minus 20, which evaluates to 4. Easy peasy. All right, there's another one we have to do. So first, let's write down a general expression. So we want all the paths starting at W ending at T. So there are two paths. This path ending on T and this path ending on T. Alright, so we have a path starting from F to U and then from U to T. Plus, because there's another path, there's a path from F to V and then a path from V to T. So we have a general expression. Now that we have a general expression, we write down an expression for specific values. So this is when it corresponds to S being 1 and T being 0. So then we have F partial U. Now F partial U is sitting on this level, so we need to know the U value, which is 2, and the V value, which is 3. And U partial T is on this level, so this corresponds to S being 1 and T being 0. And F partial V, because it's again a higher level, so we use 2, 3 here, and F partial VT at the point 1, 0. Alrighty. Again, are we given any of these values? Yes, we're given all of them. F partial U at this point is 6. U partial T at this point is 1. And then F partial V at this point is 10. And then V partial T at this point is minus 2. And it's good to put brackets there. So we have to evaluate 6 times 1 plus 10 times minus 2, which is 6 minus 20. And I'm sure you guys agree with me, it's minus 40. And that, ladies and gentlemen, is the end of the assignment. I hope you have a lovely day. You're welcome to rewatch this video again. Good day.